Actually, so in the last class, we have derived the Maxwell's equations using Maxwell's equation. We have derived the wave equation. Actually, I want to continue with the solution of wave equation in this lecture, but let's look at a numerical problem so that you will get a sense of how to use the Maxwell's equation. It will also help us in understanding the solution of Maxwell's equation. Okay, so that because during the solution we are doing some kind of an assumption, or you are having some assumptions which actually validates the point that the wave is some kind of a form. Like the electric field and magnetic field will be perpendicular. The wave is traveling in Z direction. The electric field has a component only in X direction. So all these assumptions are coming during the solution of Maxwell's equation. So to get a sense of why the assumptions are like this, let's do a problem. Okay. So problem is like this. So in a medium, characterized by sigma equal to 0, mu equal to mu 0, epsilon is equal to 4 epsilon 0, and the electric field E is equal to 20 sine 10 raised to 80 minus beta z AY cap volt per meter. Calculate beta and the magnetic field H. So this is the problem. Now here, so we want to find out the value of beta, which is this one, and also the value of the magnetic field H. Now, if you look carefully, the equation, this is actual equation of an electric field in a wave. So this is 20 sine 10 raised to 80 minus beta z AY cap. Okay. So if you look at this electric field equation, you see that this electric field equation is a function of Z, right? Means we have seen that an electric field can be a function of X, Y, Z, and T. Okay. So this electric field is a function of Z because there is a Z term here. This electric field is also a function of T because there is a T term here. And the orientation of this electric field is along Y. Why? Because you have a Y cap. So since you have a Y cap, the electric field is oriented along Y direction. The magnitude of electric field is this one, which is 20. This is the magnitude. And the electric field is varying sinusoidally because it's a sine term. Okay. And we'll see that this 10 raised to 8 is actually omega. We'll see that while deriving the solution. Okay. But only thing here you want to note is that the electric field is a function of both time and space, and the space varies only along Z. Okay. That is because you have the Z term here. Okay. So that's why you say it is a function of Z. Now you can have like X plus Y instead of Z. Then you say it's a function of both X and Y. And since there's a T term, you say it is a function of time also. So the electric field varies both in time and space, and the space variation is along Z. The orientation of electric field is along y. What do you mean by orientation? So if you are, let's say you are standing, let's say there is some coordinate system. Okay. Let's say you are standing here at some point. Okay. Now, when you stand here, let's say an electric or an electromagnetic wave propagates along your direction. Means you are standing there at one particular point. Okay. Let's say this is z axis. You are standing here at some z equal to 10 or something. Now the electric field is propagating. Okay, basically it's a wave. So let's say there is an electric field like this. Okay. Now when you stand here, although the electric field is changing along z direction because this variation is along z. So the electric field is varying along z, but you might experience a force along y direction. Okay, so there can be something like this. So that we say the orientation. So if this is y, this is just to take an example. So the orientation of this electric field is along y. So if you are standing on the field or on the wave or along the path of the wave, you will experience a force which will try to push you towards the y direction. But the if you look at the electric field wave, you see that the value of the wave is changing along z. Okay, so if I draw like this, okay, you're standing at this point, z, you're standing here, you're looking at the wave. So as you move along this way, let's say the wave, your time is constant. Let's say you have ability to stop the time. And let's say you are moving in this direction. So when you move in this direction, you will see that at some point z equal to 0, you have very low value. At some point z equal to, let's say 10, you will have this value. At some point z equal to 20, you might have this value. Okay, that means it is varying along z. Now let's assume that you have the same wave. This is z. Okay, now you are standing at one particular point, you are not moving. Let's say you are standing at z equal to 10, and the time is also changing. Okay, so now if you look at the wave, you see that at different instance of time, the value of the wave from the point you are looking is changing. So this value will be at t equal to 0. Now this wave will change its magnitude, so at some other time. Okay, so this is at, let's say, t equal to 10. So now the value of the wave is this. So you see that as you change time, or as you wait, so the basically the wave varies both in time and space. Even if you make one thing constant, you can see the variation in the other. Similarly, if you make time constant, you can see the variation in z. If you change the z constant, you can see the variation in t. This is evident from this equation. If you make this t equal to 0, the wave still varies in z. If you make z equal to 0, the wave still varies in t. So even if you make either one of them constant, you can still see a sinusoidal wave. So this sinusoidal wave is a function of both time and space. And if you are standing on its path, you will experience a force along a different direction, that is along y direction. This is what is called as the orientation of the wave. Okay, so actually, if you in all these waves there is an orientation like this. There's a vector orientation, means that there is some kind of a force which you will experience if you stand along this path. Okay, so all these waves, whichever way I have drawn, has some kind of an orientation. Now it need not be always y, or it need not be always z. It can be any arbitrary direction. But in this question, they have mentioned that the electric field is this one, and the orientation of the wave is along y. Okay, fine. So this gives you a picture of how the electric field looks like in an electromagnetic wave. And we'll also see that how the magnetic field also looks like after calculating the H of this. And we'll also calculate beta. Okay, so let's do this problem in two methods. The first method, we will use the normal differential equations and time domain form. And the second method, we will use the phasor notation or the point form, and we will see that the phasor notation is, or the point form is very easy in computing all these values. Okay, but we will do the both the things. Okay, so this is actually the harder way. Okay, fine. So what do we want to find? We want to first find H, the magnetic field H. What is the Maxwell's equation which relates E and H? Which is that equation? We know that del cross E is equal to minus dou B by dou T, which is equal to minus mu dou H by dou T. So whenever you have given either E or either H, you always, and you want to find the other term. For example, E is given and you want to find H, or H is given and you want to find E. So if either one of the terms is given, if you want to find the other, you always think of the Maxwell's equation which relates both of them. Okay, now since E is given, I can write something into E is equal to H. If H was given, then you should able to find the equation in which you should be able to write something into H is equal to E. Okay, and something in the left hand side will be a del dot or del cross. Fine. So this is the equation that we are going to use. Fine. So dou H by dou T is equal to 1 minus 1 by mu del cross E. So how will you find H? H is basically minus 1 by mu integral del cross E. Now, looking at the integral, you don't want to get afraid because you see that this is a sinusoidal wave. And del cross any sinusoidal thing is still sinusoidal, so integration will be sinusoidal. So it is easy. Okay, fine. Now let's take what is del cross E. Let's find out the right hand side, because then only you can find the left hand side. So del cross E, if you know the expression, it is AX, AY, AZ cap, dou by dou X, dou by dou Y, dou by dou Z. Okay, and here you want to say EX, EY, EZ, where EX is the component or orientation component of E along X. Similarly, EY, EZ. Now, what is EX, EY, and EZ here? You see that in this E, this has a component along Y direction, right? So the component along Y direction is actually EY. Okay. If there was a term which says something into AX cap, then this is basically this, whatever is before this AX cap is your EX. And let's say there is a something plus a Z cap, then this is something along EZ. But we don't have these terms. We have only term along EY. Okay. So all the other terms are zero. So I can write this determinant where EX equal to 0 and EZ equal to 0. And for EY, we have the expression EY is equal to 20 sine 10 raised to 80 minus beta z. Okay, let's not substitute the value now, because once if we substitute it there, then it will be like a big determinant. So let me substitute only the zero values. So I can write del cross E is equal to AX, AY, AZ cap, dou by dou X, dou by dou Y, dou by dou Z. EX is 0. I have some EY and EZ is 0. And you should note that EX, EY, EZ are magnitude along each of the direction. You don't want to put AX cap there, right? If you expand this, I hope you know how to expand the determinant. So if you expand it, you will get something like dou EY by dou Z X cap plus dou EY by dou X AZ cap, something like this. Okay. Now your E Y is equal to the current E, that is equal to 20 sine 10 raised to 80 minus beta Z AY cap. Okay. If you look at this expression, you see there is variation only along Z. Okay. Varies along Z and T and not along X. Why we are specifying it is not along X? Because you see that there is a term dou EY by dou X. So since this electric field varies only along X, the value of dou EY by dou X is, sorry, since this electric field varies only along Z and T, dou EY by dou X equal to 0. If this term would have been X and without Z, then this expression will have dou E by dou X, but will not have dou EY by dou Z. Okay. So depending on this space variation, you can make the derivative with respect to any of the other spaces equal to 0. Fine. So I can write del cross E is equal to minus dou by dou Z of 20 sine of 10 raised to 80 minus beta z. Okay. Remember, it is only the magnitude, so you don't want to write AY cap. And your direction is AX cap, which is from here. So this I have written it here. Fine. So when you differentiate, you will get as 20 beta cos of 10 raised to 80 minus beta set x cap. Okay, so you got del cross E. Now to find H, this is equal to integral minus 1 by mu del cross E dt. So if you substitute this here, you see that this is a cosine function. You have t variable here. When you integrate with respect to t, beta z, the z function, beta is always a constant. Z will be a constant when you integrate with respect to t. So I hope you know the integration. So this is minus 20 beta by mu, whatever the coefficient of t, which is 10 raised to 8. Sine cos is sine into 10 raised to 8t minus beta z x cap. Integration will not change the orientation. The orientation will be same. Right? So this is H. Now you should see a special thing here. If you look at the orientation of E, it is along Y. If you look at the orientation of H, it is along X, which are perpendicular. So in an electromagnetic wave, the electric field will always be perpendicular to the magnetic field. Always. Even if it is not along Y, but some arbitrary direction, the electric field and magnetic field will be perpendicular. So your wave looks something like this. I will try to draw this, but I am not sure I will be able to draw it correctly. Okay, so let me try this. So let's say your electric field is something like this. Okay, and your magnetic field will be something like this. Okay, I think I might not be able to draw this. Okay, where the magnetic field will be in this direction. Okay, and the electric field is in this direction. Okay, so you see that both the electric field and magnetic field are perpendicular to each other. Okay, sorry for my drawing, but I hope you understood this. So they are always perpendicular to each other, and you also see that the propagation or the change of E and H is along Z. Both are along Z. That means the wave is varying along Z, so it will be propagating along Z. Okay, so this direction is AX cap, sorry, AY cap. This direction is AX cap, and this direction is AZ cap. So the wave is propagating along E, so along Z, with this electric field and magnetic field perpendicular to each other. Okay, so this all will come again when we look at the solution of Maxwell's equation. Solution of Maxwell's equation formed as the wave equation. Okay, everything will come again, but I just want to give you a picture of using a numerical problem how actually it looks like. So this electric field and magnetic field values which is given in the problem is the actual one. It's a practical one. Okay. So this is how the wave looks like, and this is how the propagation and the orientation looks like. Okay. So we have found H. Now let's find beta. Okay. So to find beta, what we have to do is we want to find, so we also know another Maxwell's equation in which it relates H and E. Okay, and from there, if you find E, and whatever E is given in this question should match. Okay, by matching that, we'll find beta. So let's look at the next Maxwell's equation, which is del cross H is equal to sigma E plus dou E dou D by dou T. Okay. Here we are assuming sigma equal to 0 because actually the question says that it has a characteristic sigma is equal to 0. Okay, so it is easy. Fine. So I can write this as this is equal to mu into epsilon into dou E by dou T. Okay, and I can write E as 1 by epsilon integral del cross H. So if let's say this is equation number 1, if I substitute H as in equation number 1, and if I find E, then this E should match that is given in the question. Then only basically that's the Maxwell's equation, like it should match whatever electric field and magnetic field that we have calculated. Okay, let's do this. So you can write del cross H is equal to AX cap, AY cap, AZ cap, dou by dou X, dou by dou Y, dou by dou Z. Now you see H is have only one component, which is along X, right? So I can write this as Hx 0, 0. If you expand this, you get as dou Hx by dou Z AY cap minus dou Hx by dou Y AZ cap. Now, if you look at the expression of H, it varies only along Z, right? So whatever is the differentiation with respect to variable other than Z, it will go to 0. So dou Hx by dou Y is equal to 0. Implies I can write del cross H is equal to dou by dou Z of, let's substitute this equation, minus 20 beta by mu 10 raised to 8 sine of 10 raised to 8t minus beta z. Okay, and there is this AY cap from here. So if you differentiate with respect to Z, you will get 20 beta square by 10 raised to 8 mu cos of 10 raised to 8t minus beta z AY cap. This is del cross H, and from this equation, the value of E is equal to 1 by epsilon integral del cross H dt And if you substitute this value here, you will get this is equal to 20 beta square by mu 10 raised to 8. Integral of cos is sine into 10 raised to 8t minus beta z, and there is divided by 10 raised to 8 again. So this divided by 10 raised to 8 will become 10 raised to 16. So 20 beta square by mu 10 raised to 16 sine of 10 raised to 8 minus beta z ay cap. And you have found the E from H. Now both the E in the question and E that you have calculated should match. So E in question is 20 sine of 10 raised to 80 minus beta z ay cap. And these two should be equal. Okay, for these two should be equal. You see that this part and this part are already equal. So you don't want to look at any of the sign terms. And you should have this part, which is the constant, should be equal to this part, which is equal to the constant. So I can write 20 beta square by 10 raised to 16 mu is equal to 20. And mu, you know that it is equal to 4 pi, or so there is mu is equal to mu 0, which is already given in the question. And you also know the value of mu 0, which you can substitute. Okay, and you will get beta as 20 into 10 raised to 16 into mu 0 divided by 20. So this will get cancelled and take the square root. Okay, for which you will get the answer for beta. Fine. So this, I think you will get something like 2 by 3 or something. So since there is a square root, there is a plus or minus. So this is plus or minus 2 by 3. You can have either plus or minus. So implies you can write H now with actual value, and so you can substitute beta here and you can find the actual expression of H. Similarly, mu you already know. Okay, so now you can find the actual value of H by substituting the value of beta. Now you see that this is a very tedious process where you need to find the del cross, you want to integrate, and you want to find, substitute the values, etc., etc. And this is very tedious. Instead, now let's look at the next method, which is basically the phasor or the point form. Okay, and in phasor form, you know that del cross ES is equal to minus j omega mu HS. This we have derived in the last class, where ES is the phasor form, or you can write the electric field E as a real part of ES into e raised to j omega t. Right? You see that electric field given in the question is actually sine or something, but it doesn't matter. The general form is this one, in which you can substitute the values. So I can write my HS as minus 1 by j omega mu into del cross ES. And you know del cross es, it will have only component along, just like we have derived here this equation. Del cross es will have only component along x because everything will vanish. So this is equal to minus 1 by j omega mu into minus dou e ys by dou z into x cap, where eys is the component of, or I would say eys is the magnitude of component of es along x. So this you can easily find because if you differentiate eys, okay, let's see what is eys first. I think I missed that. So es I can write as 20 e raised to minus j beta z ay cap. How? Your value of e is equal to 20 sine of 10 raised to 8t minus beta z ay cap. So whatever term is there with respect to the sign or with respect to the time, it will not come in the phasor. Whatever term is along with the time, it will come as exponential to the power j multiplied by that term, and there will be the magnitude. Okay, so this, the es along y is this one. Actually, if you take this, you can write this actually as imaginary part of sorry, I can write e as imaginary part of es e raised to j. In phasor, you can take the real or imaginary, whichever is easy for you. Okay, and this es is this one. Okay, fine. So del cross es now will be equal to, just substitute the value, minus 20 beta by omega mu into e raised to minus j beta z ax cap. And so this again, I think I made a mistake. This is actually hs. Okay, and this is also hs because we have 1 by j omega mu in the multiplication factor. So that will be your hs. Similarly, to find beta, you can use the equation del cross hs is equal to j omega epsilon es. So es is equal to del cross hs by j omega epsilon. Now if you substitute hs, this is equal to 1 by j omega epsilon into del cross hs will have hs along x dou by dou z into ay cap, and you see that you can substitute this value here because this is hxs because it is along x. To substitute it here, you see that this is 20 beta square e raised to j beta z by omega square mu epsilon ay cap, and you compare these two, implies you can get the value of beta. So this will be plus 2 by 3. Okay, so just like we did in the previous method, we compare the value of actual ES and the newly obtained ES. You know all the terms. The e raised to minus j beta set will get cancelled, and you know all other terms, mu, epsilon, omega, etc. Omega is actually 10 raised to 8, which is this. This is actually omega. And you can find out the value of beta. So using the phasor notation, it is very easy because it's just division, and you don't want to do any kind of integration. Okay, fine. So this is, you can say, as an introduction to the solution of Maxwell's equation, because uh, solution of Maxwell's equation, we are going to assume all these things, that it is propagating along z direction, the electric field is oriented along x direction, magnetic field is oriented along y direction. So you should understand what these assumptions mean. Basically, it is this first page where we see that if you have an electric field expression, it have an orientation and it has a variation. The variation is basically the direction in which the wave is propagating. So along that direction, the electric field will change its values. And the orientation is the direction in which you will experience a force when you stand in the path of the wave. So you might be experiencing a force along y direction, but you can see the change in the electric field only along the z direction. So I hope you have understood this problem. So make sure you do it your own so that you will understand it better. You try to solve it by your own, then only you will know how to solve it easily. Okay, fine. So I think it is a good time to stop the class. Let me take the attendance.